Tim Mithro-Ansel has come all the way from Australia to talk to us about dissecting HDMI and developing an open and FPGA-based capture hardware for sharing talks outside of the room. And he will be explaining how to dissect it, and I'm looking forward to hearing the talk in a second. So please give Tim a warm round of applause again. Thank you.
Okay, hi, I'm Tim, and in theory if my slides change you would see that. And I kind of have too many projects, and I'm going to be discussing one of them. This is another project that I gave a lightning talk on earlier. If you didn't see it, it's an ARM microcontroller that goes in your USB port. People wanted to know when to hack on it. Tomorrow at 2 p.m. apparently. So first I want to say is I'm a software developer. I'm not a hardware designer. I'm not an FPGA developer. I'm not a professional in any of that. I develop software for full time. So this is my hobby. As well, this information comes from a couple of projects that I started, but a lot of other people did the majority of the work, and I'm just telling you about it because they're too shy to come up and talk about it themselves. So a big thank you to all these people who've helped me in various ways regarding this. And these slides, any of the blue things are links. So if you're playing along at home, you can get to them by that URL and click on these things. And there's probably other people I've forgotten who are not on this list. I'm very sorry. So this title of this talk could be called Software Guy Tries Hardware and Complains. I've had a really hard time figuring out what to call this talk, and you'll see some other attempts at naming this talk better. So a bit of history. How did I end up doing HDMI stuff? So Tim Videos is a group of projects which are trying to make it easy to record and live stream user groups and conferences, like this event. However, we want to do it without needing the awesome team that is doing the recording here. These guys are really, really organized and professional. We want to do it where people have no experience at all with AV and can just make it happen. And so this is how you record a conference or user group. I'm going to be talking about these two things here, the HDMI to USB devices that we created. They're used in our setup both for camera capture and for capture of slides. And so the HDMI USB is FOSS hardware for doing HDMI capture, and actually has a bit of history with the CCC because it was inspired by a speaker who spoke here. Bunny spoke on his NETV board, which was a FPGA man-in-the-middle attack on HDCP secured links. His talk is really awesome. It's going to be that talk is way more technical than mine and gives you some really awesome details about the cool things he did to make that work. Mine is much more basic. You don't need much experience with HDMI to follow my talk. And so Out of Ice works like his does, except his was deliberately designed to not allow capture. Our design allows capture. It effectively mans in the middles the presenter's projector between the presenter's laptop and the projector, and provides a high-quality capture out the USB 2 port. It used an FPGA to do that. This is because using FPGA makes hardware problems, software problems, and as I said, I'm a software developer. I prefer software problems to hardware problems. And The way it kind of works is it appears as a UVC webcam, so that you can use it with Skype or Hangouts or any of those things without needing any drivers on sensible operating systems like Macs and Linux. On Windows, you need a driver that tells it to use the internal driver. It's kind of weird. And also serial port, because we have the ability to switch which input goes to which output. It's kind of like a matrix. And so this is the open source hardware we designed. It's in KiCad. You can find it on GitHub. I'm quite proud of it. It's quite a good little kit. We don't use all the features of it yet, but it's pretty awesome. And it's in use. We use this technology to capture at a bunch of conferences. PyCon in Australia, linuxconf.au in Australia. As I said, I'm Australian. DebConf, though, are not Australian. They used it in, in South Africa, I think. And there are a whole bunch of other people around the world who are using this, which is pretty awesome. The main reason I wanted it to be open source was so that other people could use them and learn from it and fix problems, because there are lots of problems we've run into. The other thing is this is all full of Python. We do use FPGA to Python to create the firmware for the FPGA and all these other areas. If you want to find out more about that, go to my talk at PyCon AU, which was recorded with the very device I'm talking about, which is kind of cool. Oops, sorry. But as I said, this is going to include lots of problems. The first one is people still use VGA. This kind of makes me sad. Because VGA is not HDMI. It was invented in 1987, and it's an analog signal. Well, HDMI shares some history with VGA. You can't use the same techniques for capturing HDMI that you can VGA. So why do you still use it? It's old and bad. We developed a VGA expansion board to effectively allow us to capture VGA using the same thing. By developed, I mean we have designs and some exist, but nobody's actually finished the firmware to make them work yet. So I'd love help there. There's also another problem. I want to do this all open source, as I said. The HDMI ecosystem has commercial cores you can buy, and they work reasonably well. But you have to buy them, and you don't get the source code to them, or if you do get the source code to them, you can't share them with other people. As well, I wanted to be open source because we wanted to solve all those problems that people have when plugging in their laptop and it not working. And the commercial cores aren't designed to allow us to give the ability to do that, solve those problems permanently. So we create a new implementation. As anybody who's ever done a re-implementation or a new implementation of something, it means that you've got new bugs, which I will describe quite a bit. So this talk could be called Debugging HDMI rather than Dissecting HDMI, because it includes a lot of information about how things went wrong. Okay. So that's kind of the introduction of why we're here and why I'm talking about this. So how does HDMI work? Well, HDMI is actually reasonably old now. It was created in 2002. It's based on the DVI specification. DVI was created in 1999. So DVI is 17 years old. And DVI was designed to replace VGA and shares a lot of similar history. HDMI is backwards compatible with DVI electrically and protocol-wise, but uses a different connector. And so this is an HDMI connector. You've probably seen them all before. If you look closely, you'll see that there are 19 pins on the HDMI connector. That's pin 1. So what do all these pins do? Well, there are 5 pins which are used for ground. There's 1 pin which is used for power. It gives you 5 volts at 50 milliamps. This isn't much to, you can't do much with 50 milliamps except maybe some type of adapter, converter, or power whole microcontroller. Some Chinese devices try to draw like an amp from this. That's not very good. So that's another thing you should watch out for. There are 3 high-speed data pairs which transmit like the actual video data, and they share a clock pair. So that's these pins here. And then there are 5 pins which are used for low-speed data. And so that's all the pins on the HDMI connector. You might have noticed that there was a whole bunch of different things I said there. And you need to actually understand a whole bunch of different protocols to understand how HDMI works. There's a bunch of low-speed ones, and there's a bunch of high-speed ones. I'm not going to talk about all of those protocols because there's just too many to go into an hour talk. The low-speed protocol I'm not going to talk about is, say, CEC or audio return, and I'm not going to talk about any of the auxiliary data protocols that is high-speed, or HDCP. If you want HDCP, go and look at Bunny's talk. It's much better than mine, or Ethernet. What I will be talking about is the EDID and DDC protocols. The 8B10B encoding of the pixel data, and the 2B10B encoding of the control data. Interesting enough, this is actually DVI. I'm not telling you about HDMI, I'm really describing to you how DVI works. So again, many titles. So starting with the low speed protocol, EDID or DDC. I'm going to use those 2 terms interchangeably. They've been so confused now that they are interchangeable, in my opinion. This is something they inherited from VGA. It was invented and added to VGA in August of 1994. It was for plug and play of monitors, so that you could plug in your monitor and your graphics card would just work, rather than requiring you to tell your graphics card exactly what resolution and stuff your monitor worked at. It uses I2C and a small EEPROM. These are the pins that it uses. 15 is the clock pin, and 16 is the data pin. And then it uses the ground, and the 5 volts is used to power that EEPROM. And in some ways, it also uses 19, because 19 is how you detect that there's something there to read from. It uses I2C. I2C is a low-speed protocol that runs at either 100 kilohertz or 400 kilohertz. Technically, EDID is not I2C, but it is. It only supports the 100 kilohertz version, though in theory, everything on this planet can be read at 400 kilohertz. It's also very well explained elsewhere, so I'm not going to explain in detail what I2C is or does or how to implement it. The EEPROM is a 24 series. It's found at I2C address 50. It's 8 bits in size, which gives you 256 bytes of data. Again, this EEPROM and how to talk to it is very well described on the internet. So I'm not going to describe it here. If you've used EEPROMs over I2C, it's likely you've used a 24 series EEPROM. Probably bigger ones. 256 bytes is pretty small. So like a 16 width one. But EDID only supports the 8 bits ones. The kind of interesting part of EDID is the data structure. It's a custom binary format that describes what the contents of the EEPROM is. Again, Wikipedia has a really good description of this, so I'm not going to go into much detail. but the important things are that it describes the resolution, frequency, and format for talking to the monitor. This is really important because if you try and send the wrong resolution, frequency, or format, the monitor's not going to understand it. And so this is kind of what EDID is used for. So this is where things start getting a bit hairy. Presenters come up to the front, and the first question you'll see anybody ask is, what resolution do I use? And they get a panel like this, which has a bazillion resolutions selected. And the thing is, despite your monitor saying that it supports many formats, they lie. And it turns out that projectors lie a lot more than normal displays. I don't know why they're special. And so this is what a supported format looks like. It's really great. As well, I care about capturing the data. And so I want things in the format that is easy for me to capture. I also don't want to be scaling people's images and text because scaling looks really bad. So if somebody selects like a really low resolution and we scale it up, it looks really horrible. It makes text unreadable, and presenters are very renowned, especially at technical conferences, for using tiny, tiny fonts. And so we need as much resolution as we can. And so how we solve this is we emulate our own EEPROM in the FPGA and ignore what the projector tells us it can do. We tell the presenter that this is what we support. You might notice that it kind of solves the problem of what resolution we do. Offer a single solution, offer a single option. It makes it very hard to choose the wrong one. So that's good, we've solved a problem. No, we haven't solved a problem. We were recording PyCon-AU, and we found that some Mac laptops were refusing to work. To understand the cause of this, you need to understand a little bit about how the world works. There are two major frequencies in the world, 50 Hertz and 60 Hertz. 50 Hertz is mainly used in the rest of the world, and 60 Hertz is used in America and Japan and a few other places, but that's kind of very rough thing. Laptop, sold in Australia. Australia's 50 Hertz, it's part of the rest of the world. You'd think that the laptop could do 50 Hertz. Plus, everything's global these days, right? I can plug in my power pack for my laptop in the US or Australia. So, like, it should work everywhere, right? No, sad. So, we solved it by claiming that we were American and supporting 60 frames per second rather than 50 frames per second. So I guess display with American accent. We deployed this hotfix on the Friday evening, and on Saturday, all the problems that we were having on Friday went away. So this is kind of the power of an open source solution and having complete control of your hardware. Nowadays, we actually offer both 60 and 50, because for display capture, if you're displaying stuff at 50 frames per second, you're probably speaking a lot faster than I am. And it's really weird. These 128 bytes are really hard, and the #1 cause of why a person's laptop can't talk to the projector. Gets a trophy. To try and figure out why that is, we created edid.tv. It's supposed to be a repository of edid data. It was a summer of code project, Python, Django, Bootstrap, and an edid grabber tool that you can run in your laptop. I'd love help making this work better. It hasn't had much love since the summer of code student made it work. But it'd be really nice to have an open database of everybody's edid data out there. There are a bunch of closed ones. I can pay to buy one, but I'd really love to have an open one. As well, maybe we don't need the whole capture solution. Maybe we can just override the EDID. And so the C3 VOC here actually developed a version that overrides EDID for VGA. I have a design which works for HDMI. It just uses a low-cost microprocessor to pretend to be an EEPROM. As well, DisplayPort is not HDMI. Don't get the two confused. They're very, very different protocols. They have an auxiliary channel like EDID and CEC. I have boards to decode them here at CCC. So if you're interested in that, come and talk to me, because we'd really like to do similar things for DisplayPort. So that's the slow speed data. What about high speed data? So each pixel on your screen is basically 3 colors in DVI standard, red, green, blue. And each one's a byte in size. Each of the colors is mapped to a channel on the HDMI connector. And so you can kind of see the red and the green and the blue channels. Each channel is a differential pair. You get a plus and a negative and a shield. They use twisted pair to try and reduce the noise reception of these, because these are quite high speed. And they have a dedicated shield to try and, again, reduce the noise that is captured. And so this is kind of where it gets the differential signaling part of the TMDS, that is the kind of code name for the internal protocol that is used on the high-speed data. They also, all those channels share a clock. That clock is called the pixel clock. But each of these channels is a serial channel. It transmits data at 10 bits. Every 10 bits, every clock cycle, there are 10 bits of data transmitted on each of these channels. So there's a shared clock, and each of the channels is running at effectively 10 times that shared clock. And so this is kind of what the whole system looks like. You have your red, green, blue channels. You take your 8 bits of input data on each channel, and you convert it to the 10 bits that we're going to transmit, and it goes across the cable, and then we decode on the other side. So the question is, what does the 8-bit to 10-bit encoding look like, and how do you understand that? It's described by this diagram here. It's a bit small, so I'll bring it up. This is what it looks like. Yeah, sure. What? This diagram, I've spent hours looking at this, and it is an extremely hard diagram to decode. It's very, very hard to understand. And it turns out the encoding protocol is actually quite easy. It's 3 easy steps, approximately. And so I'm going to show you all how to write an encoder or decoder. That diagram is just for the encoder. They have a simile diagram that is not the inverse of this for decoding. Again, almost impossible to read. So the 3 steps are, first we're going to do control or pixel, choose which one to do, and then we're going to either encode control data or encode pixel data. So a couple of important points to go through first. The input data, no matter how wide it is converted to 10-bit symbols. Data goes to symbols. When we're talking about them being transmitted, we talk about them symbols. When it's decoded into pixels, we talk about them in data. As well, things need to be kept DC balanced. So I've rushed ahead. The question is, why 10 bits? our pixels were 8 bits. I will explain why in the pixel data section, but it's important that all our symbols are the same size. We're always transmitting 10 bits every clock cycle. Keeping DC balanced. Long runs of ones or zeros are bad. There are lots of reasons for this. I tend to think of it like HDMI isn't AC coupled, but you can kind of think of it like AC coupled. It's not to recover clock. We have a clock pair that is used to give our clock signal. There are lots of lies on the internet that say that the reason we want to keep DC balanced is because of clock. But no, that's not the case. So what does DC balance mean? A symbol which has lots of ones or lots of zeros is going to be considered DC biased if it has more ones than zeros. And this is kind of what it's like. This symbol here has lots of ones, and so if you add up all the ones, you can see it's got quite a positive bias. If it was inverse and had lots of zeros, it would have a negative DC bias. And so that DC bias over time causes us problems. So those are the two important things we have to keep in mind when looking at the rest. So the first thing we need to figure out is, are we transmitting control data or pixel data? Turns out that what is happening in your display is we're transmitting something that's actually bigger than what you see on your screen. This is not to scale. The control data periods are much, much smaller. The control data is in orange and the pixel data is in purple, pink. So why does this exist? It exists because of old CRT monitors. And for those in the audience who were kind of born after CRT monitors, this is what they look like. And the way they work is they have an electron beam that scans across, highlighting the phosphorus. This electron beam can't just get back to the other side of the screen straight away, or get back to the top of the screen. And so these periods where we're transmitting control data was to allow the electron beam to get back to the location where it needed to start transmitting the next set of data. And so that's why it exists. Why do we care? Because the encoding schemes for control and pixel data are actually quite different. This is the main difference. I'm going to come back to this slide a bit later. But again, an important thing to see here is that despite the encoding scheme being quite different, the output is 10 bits in size. So that first step, choosing whether it's pixel or control data, is described by this bit of the diagram. You might notice it's not the first thing in the diagram. So how do you convert control data to control symbols? First, we need to know what control data is. There are 2 bits. There's the H-sync and the V-sync signal. They provide basically the horizontal and vertical pixel sizes. They're kind of left over from VGA. We don't actually need them in HDMI or DVI to know where the edges are, because we can tell the difference between control and pixel data, but they kind of still exist because of backwards compatibility. This means that we have 2 bits of data that we need to convert to 10 bits of data, so it's a 2B, 10B scheme. And how they do it is they just handpicked 4 symbols that were going to be these control data symbols. These are the 4 symbols. There's some interesting properties with them. They're chosen to be DC balanced. They roughly have the same number of zeros and ones. So we don't have to worry about the DC bias of these symbols very much. They're also chosen to have 7 or more transitions from 0 to 1 in them. This number of transitions is used to understand the phase relationship of the different channels. So if you remember this diagram, we have a cable going between the transmitter and the receiver. These, again, very high-speed signals, and even if the transmitter was transmitting everything at the same time, the cable isn't ideal and might delay some of the symbols, the bits on one channel longer than others. And so by having lots of these transmissions, we can actually find the phase relationship between each of the channels and then recover the data. And so that's why these control symbols have a large number of transitions in them. More on that later when we get to implementation. And I'm running out of time. So this part of the diagram is the control data encoding. What about pixel data to pixel symbols? Again, in DVI, each channel of the pixel is 8 bits. And the encoding scheme is described by basically the rest of the diagram. But again, it's actually really, really simple. This encoding scheme is called 8B10B because it takes 8 bits, converting it to 10 bits. However, there's a huge danger here because IBM also invented an 8B10B scheme that is used in everything. This is used in DisplayPort, it's used in PCI Express, it's used in SATA, it's used in pretty much everything on the planet. This is not the encoding TDMS uses. You can lose a lot of time trying to map this diagram to the IBM coding scheme and going, these are not the same. That is because they're not the same. This is a totally different coding scheme. So encoding pixel data is a 2-step process. I did say it was 3-ish steps to do this. The first step is we want to reduce the transitions in the data. And so how do we do this? Why do we do this? Is because this, again, is a high-speed channel. We want to reduce the crosstalk between the lanes. They're actually quite close to each other. And so by reducing the number of transitions, we can reduce the probability that the signal propagates from one channel to the next. And how we do it? We're going to choose one of 2 encoding schemes. An XOR encoding scheme or an XNOR encoding scheme. So how do we do the XOR encoding scheme? It's actually pretty simple. We set the encoded bit same as the first data bit, and then the next encoded bit is the first encoded bit XORed with the data bit. And then we just repeat until we've done the 8 bits. So this is how we do the XOR encoding. The XNOR encoding is the same process, except instead of using XOR, it uses XNOR. Then how do we choose which one of these to use? If the input data byte has fewer than 4 ones, we use the XOR. If it has more than 4 ones, we use the XNOR. And then there's a tiebreaker if you have even. The important thing here is that this method is determined by the data byte only. There's no hidden state here or continuous change. Every pixel has a 1-to-1 mapping to an encoding. And then we append a bit on the end that indicates whether we chose XOR or XNOR encoding of that data. And so that converts our 8 bits input pixels to 9 bits of encoded data. Effectively, our 8-bit encoded sequence, and then 1 bit to indicate whether we chose XOR or XOR-NOR encoding for that data bit. So that's it there. This encoding is actually very good at reducing transitions. On average, we had roughly 8 transitions previously. Now we have roughly 3-ish, so it's pretty cool. I have no idea how they figured this out. I'm assuming some very smart mathematicians were involved, because discovering this is beyond me. And that describes the top part of this process. This is where in the TMDS, the transition minimization comes from, that step there, the encoding process. But there's still one more step. We need to keep the channel DC balanced, as I explained earlier. And how can we do that? Because not our pixels aren't guaranteed to be a 0 DC bias like our control symbols are. We do it by keeping a running count of the DC bias we have. And then if we have a positive DC bias and the symbol is also positively biased, we invert it. Or if we have a negative DC bias and the symbol has a negative DC bias, we invert it. And the reason we do this is because when we invert a symbol, we convert all the ones to zeros, which means a negative DC bias becomes a positive DC bias. And so, as I said, we chose, because we are already negative and the thing was negative, we convert it to plus. It means that we're going to drive the running DC bias value back towards 0. We might overshoot, but the next stage will keep trying to oscillate up and down, and on average over time we keep a DC bias of 0. And as I said, then to indicate whether or not we inverted or kept the straight through, or we inverted, we add another bit on the end. And so that's how we get our 10-bit encoding scheme. We have the 8 bits of encoded data, then 1 bit indicating whether or not it used XOR, XNOR encoding, and then 1 bit to indicate whether or not we inverted the symbol. And so that describes this bottom part of the chart. And now you can see partly why this chart is kind of confusing. It's no way in what I think of as a logical diagram. This might be how you implement it in hardware if you already understand the protocol, but not very good diagram for explaining what's going on. And as you see, it's actually pretty simple. And in summary, this is the interesting information about the 2 different encoding schemes. Because we minimize the transitions in the pixel data, we can actually tell control data and pixel data apart by looking at how many transitions are in the symbol. If it has 6 or more transitions, it must be a control symbol. If it has 4 or less, it must be a pixel symbol. So you now know how to encode TDMS data and how to decode TDMS data. Because if you want to decode, you just do the process backwards. Congratulations. So how do you actually implement this? Well, you can just write the XOR logic and a little counter that keeps track of the DC bias and all that type of thing in the FPGA. I'm not going to describe that because I don't have much time, but if you follow the process and that I've given you, it should be pretty easy. And this is what we use currently. You could actually use a lookup table. What we're doing is converting 8 bits of data to 10 bits of data. That is a lookup table process. Pretty easy. FPGAs are really good at doing lookup table type processes, and it also allows you then to extend this system to those other protocols like the 4B, 10B that is used for the auxiliary data. So we're looking at that in the future. It uses a few more resources, but is a lot more powerful. And so this is kind of what your encoder will look like and your decoder. It's quite simple. Takes in your 10 bits of data and outputs either your 8 bits of pixel data or your 2 bits of control data, and a data type. This is kind of what, if you went into our design and looked at it at a high level in the schematic, you'll probably see a block that looks like this. The encoder is slightly more complicated because you also have the DC bias count that you have to keep track of. But again, the data goes in and the data comes out. That's simple, right? And yeah, this kind of extends to auxiliary data. Or if you get an error, like there are 124 symbols that you can have in 10 bits of data. Not all of them are valid. And so if you get one of these invalid symbols, you know you have an error. However, things happen quite quickly when you times them by 10. And so our pixel clock for 640 by 480 is 25 megahertz. When you times that by 10, you get 250 megabits per channel. When you're doing 720p, you're doing 750 megabits per channel, and 1080p is 1,500 megabits per channel. And FPGAs are fast, but they're not really that fast at a range that I can afford to buy. I'm sure the military has ones that go this fast, but I'm not as rich as them. But they do include a nice hack to solve this, and they're called SerDes. They basically turn parallel data into serial data. This is what the blocks look like. You give them your TDMS parallel data, and they convert it to high-speed serial data for you. They're a little bit fiddly to use, and your best option is to go and find a person who's already configured this for your FPGA and follow what they do. Mike Hamsterfield has a really good documentation on how to use these in the Spartan 6. These are also unique to your FPGA, so different FPGAs are going to have different control schemes. But if you're using a Spartan 6, then go and look at what Mike Hamsterfield is doing for configuring these. And so, I remember how I said our system has a serial console. Because we have this system, we can actually delve quite deep into what's happening internally in the system and print it out. And so this is debugging from one of our systems. You can see the first thing is the phase relationship between each of the channels. The next one is whether we're getting valid data, and then on each of the channels. And then we've got the error rate for that channel, whether all the channels are synchronized, and then some resolution information. You can see that this has got a 74 megahertz pixel clock. And there are 3 columns because there's red, green, and blue channels. So this gives us some very interesting debugging capabilities. If you plug in a cable and you're getting errors on the blue channel, but nowhere else, it's highly likely there's something wrong with that cable. This is a very powerful tool that allows us to figure out what's going wrong in a system. And it's something you can't really get with the commercial versions of this. But what about errors? Everything I'm talking about now is a little bit experimental. We haven't actually implemented this, but it's some ideas about what we can do because we now have complete control of our decoder. So as I said, there's 124 possible choices for 10-bit symbols, of which 460 are valid pixel symbols, 4 are valid control symbols, and 560 symbols should never, ever be seen no matter what. That's like 56% of our space that should never be seen. But it's actually better than that. We know because of the running DC bias that there are 256 valid pixel symbols at any one point. You can't have if you've got a negative DC bias, you can't have a pixel symbol which continues to drive you negative. And so actually 74% of our space at any one time is not allowed to exist. This means that a huge number of the invalid symbols are only near one other valid symbol. And so we can actually correct them. We can go, this symbol must have been this other symbol because it's not a valid symbol. It must be a bit error from this other symbol. So we can correct these errors. And this is quite cool. We can correct about 70% of single-bit flip errors in pixel data. But sadly, there is some that we can't. But we can detect that we got an invalid pixel data. So the fact that there's an error is important. So in this case, we've got 2 pixels that we received correctly, and we got a pixel that we know is an invalid value, and then 2 more pixels that we received correctly. So you can imagine this is a blue channel. So the first ones were very, very blue, not very blue, and then there's the decoded value for this is very, very blue, like very light blue, and then some not other ones. This looks really bad, right? This was probably a whole blue block. 1 pixel difference of that big, that size is probably not a valid value. And so we can cover them up. We can go the 2 pixels either side and average them and fix that pixel. So this allows us to correct a whole bunch more of errors that are occurring. And as we're about to take this data and run it through a JPEG encoder, this doesn't actually affect the quality of the output all that much and allows us to fix things that would otherwise be giant, glaring glitches in the output. And so that's some interesting information about how you do TDMS decoding and how we can fix some errors. The thing is, we can do even better than this because it's an open source project. Maybe you have some idea about how we can improve the SerDes performance. Maybe you have some idea about how to do TDMS decoding on a much lower powered device than we use. It's open source. You can look at the code and you can improve it. And we'd love you to do it. And the thing is that I have lots of hardware but not much time. If you have lots of time and not much hardware, I think I can solve this problem. These are links to the HDMI to USB project and the Tim Videos project, and all our code, our hardware, everything is on GitHub under open source licenses. And here's some bonus screenshots that I wasn't able to fit in other locations. You can see these are small errors. That one was kind of a big error. This is what happens when your DDR memory is slightly broken. Yeah. But, yeah. And that is my talk.
Excellent. Thank you very much, Mirtho. And as you've noticed, we have a couple of microphones standing around in the room. If you have any questions for Mirtho, please line up behind the microphones and I will allow you to ask the questions. We have a question from the internet.
Yes, thank you. Do you know if normal monitors do similar error recovery or hiding?
I know of no commercial implementation that does any type of error correction. The solution for the commercial guys is to effectively never get errors. They can do that because they don't have to deal with the angry speakers on the ground going, why does my slides look weird? And as well, they're probably working with better quality hardware than we're using. we're trying to make things as cheap as possible, and so we're pushing the boundaries of a lot of the devices we're using, so we're more likely to get errors than they are.
We have quite a lot of questions, so remember, questions, not comments. Microphone number 1, please.
Yes? Sorry, I don't quite understand what's going on.
Do we have translation?
Audio problem? I'll be around afterwards if you want to chat to me.
And we might do that, write to you on the computer afterwards. Second question from microphone number 3, please.
Hello? Yes, can you determine the quality of a HDMI cable, for example, by measuring bit error rate of each 3 pairs and maybe also some jitter on the clock and that kind of?
Yes, we can. The quality of a HDMI cable should be their 0-bit errors. So anything that has non-0-bit errors, we chop up and throw away. This gets interesting when you have very long cables. We can actually see that the longer the cable is, the harder for them to keep 0-bit errors. So yes, we can kind of judge the quality of the cable, but it's also hard because it depends on what the sender is doing. If the sender is of a lower quality and the cable is low quality, you might get bit errors. But if the sender is of a high quality and the cable is of a lower quality, they might cancel each other out and still be fine. And so we can't just go, this is a good cable, because we don't actually have any control over how powerful our sender is on this device. If we could kind of turn down the sender and see where things start going wrong, that would be pretty cool. If anybody wants to look at building such a device, I would love to help you do that.
We have another question from microphone number 5.
Your hardware, the HDMI to USB hardware,
yep.
Is it available for simply ordering, or has it to be soldered by hand? Or
you cannot solder this board by hand unless you're much, much better than I am. It uses ball grid array parts because it's an FPGA. This is one here. You can buy them. We're working with a manufacturer in India who builds them for us. We worked with them and it was pretty awesome. We're also working on new hardware. I've got a whole bunch of FPGA hardware down here that you can come have a look at, and I'll probably move it out into the hallway afterwards. Again, if you're interested in the hardware and you have a use case, chat to me, because I like to solve problems of people not having hardware, and my employer pays me too much, so I get to use my discretionary funds for helping out people doing open source stuff.
We have at least 4 more questions. Microphone number 2, please.
Do you think it would be possible to get an 180p image out of the open source hardware board you produce?
Yes, I do, but it requires us to do some hard work that we haven't had time to do yet. And for us, 720p at 60 frames per second is good enough. The USB USB connection is limited in bandwidth because we don't have a H.264 encoder, we only have MJPEG. If somebody wants to write us a open source, say WebM rather than H.264 encoder, that might start becoming more interesting. We also have Ethernet, gigabit Ethernet on this board. It should be pretty easy to stream the data out to Ethernet. Again, need help. The Ethernet controller works. We can telnet into the board and control it via telnet. We just need somebody to actually connect the data and the high-speed data side up. We use it for debugging and stuff. So yeah, Mike Hamsterfield, again, really big thank you to him. He is an amazing designer. He built 1080p 60 that is a little bit out of spec, but actually works really well on hardware that is almost identical to us. He also did the DisplayPort, like a 4K DisplayPort, which we can do on our board. So if you only need one or two of the 1080p things, DisplayPort connectors can be converted to HDMI quite easily, and you can do that on them. So yes, I think it's possible, but again, open source, hobbyist, need developers.
We'll take one question from the internet.
Thank you. Have you considered JPEG 2000?
No, I have not. And the main reason is that I want to be a webcam. I want to pretend to be a webcam. The UVC standard, which is the USB webcam standard, does not support JPEG 2000. There's no reason we couldn't support JPEG 2000 when connected to Linux. Like, we could fix the Linux driver to add JPEG 2000 support. Again, I don't know if there's any good open source FPGA implementations of JPEG 2000. So that's also a blocker. But yeah, if you're interested in helping out, come and talk to me. As I said, I would very much love to chat to you and solve the problems you're having with getting going. As well, we have t-shirts. I'm wearing a t-shirt that we have, and I will send anybody who contributes a t-shirt, whether that's fixing our website, helping with documentation, helping people on IRC get set up, anything. You don't need to be an expert on FPGA stuff to help out. And we also are working on a little project to run MicroPython on FPGAs. So if you're really into Python and you like MicroPython, I would love to help you help us do that. It's kind of working. We just need more peripheral support. So
we have two more questions from microphone number 1.
So is there some sort of dedicated processor on that board, or do you use like a microblaze in the FPGA? We
use an open source soft core, one of 3. We can change which soft core we're using with a command line flag. We're using either the Lattice Myco 32, which was produced by Lattice Semiconductor. We can use the OpenRISC 1K, or we can use a RISC-V processor. We generally default to the LM32 because it's the most performance for least FPGA resource trade-off. But if you like RISC-V or OpenRISC 1K better for some reason, say you want to run Linux on our soft core, then you can do that with a one-line command line change. We're looking at adding J-Core support in early next year. J-Core is quite big though compared to LM32, so it probably won't fit on some of the very small devices.
So it's a Lattice FPGA you have?
It's a Spartan 6 FPGA, and our new boards will probably be RTX 7, but we're still in the process of making them exist yet. I've also been working with Bunny's NETV2, porting our firmware to that, which has been really awesome. He's doing some cool work there, and he's kind of inspired this whole development by showing that, yes, you could do this, and you shouldn't be scared of it.
Good. One more question from microphone number 1.
Yes. Do you have any plans for incorporating HDSDI into your platform?
Yes and no. We have plans and ideas that we could do it, but HD SDI and all of the SDI protocols are much harder for the consumer generally to access, and we want to drive the cost of this down to as low as it can go. And HDMI is a consumer electronic thing. You get it on everything. You get it on your like $5 Raspberry Pi. HDMI is probably a really good solution for this. We haven't developed any SDI cores or anything like that, so I can't tell you like that we're doing anything there. But if somebody is interested, again, I like to remove roadblocks, and we would love to have people work on that.
We have one more question from the internet, and we have 2 minutes left.
Okay, thank you. The question is not related to HDMI, but to FPGAs. FPGAs are programmed in a high-level language, like Verilog, or after simulation you compile. So every vendor has created his own compiler for its own hardware. Are you aware of a move to open source compilers or to independent hardware? And do you see a benefit in open source FPGA compilers?
Yes. If anybody knows about FPGAs, you'll know they use proprietary compilers, and these proprietary compilers are terrible. I'm a software engineer. If I find a bug in GCC, I can fix the bug. I've got those skills, and I can move forward, or at least figure out why the hell the bug occurred. That is not the case with FPGA compilers. The FPGA compiler we use is non-deterministic. You can give it the same source code and it produces different output. I'd love somebody to reverse engineer why that occurs, because I've removed all the randomness from random sources from it, and it still manages to do it. I'm really impressed. So Clifford has done an open source FPGA toolchain for the lattice ice stick things. He said he's going to work on the Atrix 7 FPGAs. Please donate to him and help him. I would if that exists, I owe people like a bazillion beers, because the sooner I can get off proprietary toolchains, the happier I will be, and it'll make my hobby so much nicer. So please help him.
And do give Tim a big round of applause.